Is it also a straight line or a horizontal line?
It won't be a horizontal line. Remember that acceleration is the slope of this graph. So if this is horizontal, that means the velocity is constant, which says the acceleration is 0.
Negative 30 at 10 seconds.
Okay? Well, there, that's negative 30. And then connect the dots. I also know that it's 0 at 5 seconds.
Yeah.
2, 3, 4, 5. Something like that. And then displacement first time. There are a couple ways of approaching this. Anyone in here had calculus? Okay, got a couple of you. We're doing antiderivatives here. I don't know if that helps you. This is constant, that's linear. That potentially gives you a hint at what this shape will be over here. Let's take it piece by piece then. At what time is the car the farthest away from its starting point?
5 seconds.
Yeah, that's the point when it stops. It's going away and then comes back. So at 5 seconds, it's the farthest away. How far away is it at that point?
75 meters.
Yep, so that's 75 meters there. What is the displacement when the problem starts?
Should be 0.
And when the problem ends?
Also 0.
All right, so I got 3 data points right there. I got a couple other clues. I know that this graph is a graph of my slope. This is the graph of the slope of this. What's written over there. Which tells me my slope starts out big, and then my slope goes to 0. And then it gets more negative. What does a positive slope look like? So 1 hand gesture, 2 hand gestures. Can we get a third? I think we fly out of the way, or are you just doing the gesture? Okay.
To the right.
All right. And negative slope? All right. So I know it's 0 at this point, and it's steep here, but then gets less steep because my velocity gets smaller, which means my slope gets smaller. And that is really badly done. 2, 3, 4, 5. Apparently I didn't evenly space that. What is the shape? Yeah, it's a parabola. The other clue that it should be a parabola is right here. That's my equation right there for the displacement. The acceleration is constant. My initial velocity is a constant in this problem. And so basically it's a quadratic equation, and quadratic equations plot as parabolas. Questions to hear? Let's put this in a bigger context. Physics is about modeling the world so that we can predict the future. It's all about being able to tell the future. And so all we're doing right now is just coming up with the language to describe motion. When we get to chapter 4, we'll figure out ways of finding acceleration without using those. one more question here before we take a break. What is the final position? What is the final position of the car?
Back at the initial position.
Yeah, that is true.
Not what you're looking for, then.
No, I'm looking for a number.
Would be 0 if it's the same.
No, not necessarily. When would it be 0? It's not because we're back where we started.
If the initial was at 0, or if it started at 0.
In essence, we're there. Based on what I gave you here, there's not enough information to actually answer the question of what's the position. I never told you where the origin was. All I told you is where the starting point was. Now, often in a problem like this, and I'm trying to remember if I corrected it on the master set hint. If I don't tell you the initial position, you can find displacement, but you have no idea what the final position is if you don't know where it started. You need to know the position at some point in the path. So, in this, oftentimes when you're doing a problem, you get to decide, at this point, no, but when we get especially into chapter 4 and beyond, actually chapter 3 and beyond, you start to decide where the initial positions are and what coordinate system you're going to be using. Anyway, on that cheery note, let's take a 5-minute break, stretch your legs, calm down a little bit, get ready for the next part. See if I can get my mask adjusted better. One last follow-up to the problem that we just did. An alternate way of doing it. This is sort of the tedious plug and chug, and it's fine if I'm only dealing with 6 seconds. I have done problems that last over 40 seconds, in which case this would just be torture to do it this way. But we start out at 30 meters per second. My acceleration is -6 meters per second squared, which means that my acceleration is -6 meters per second. Every second that passes by, my velocity changes by -6 meters per second. So after 1 second, well, the change is -6, so what is my velocity after 1 second?
Meters per second?
Yep, oops, duplicated units there. So 24, after 2 seconds.
18,
3 seconds,
12,
4,
6,
5,
0,
6.
-6.
If you kept going, By the time you get to 10 seconds, you better be at negative 30, which is what we calculated before. Also, at what time did it stop? Well, that's right there. Over the first 6 seconds, what's the average velocity? And how would you find it?
Just add them all together about by 6.
I would not recommend that. What was wrong with what he said? Let me ask you, how do you average numbers? Why were you dividing by 6?
You divide by
Because you-
7.
Yeah,
There's
there's
never
7
count
numbers
for
here.
0.
Yeah, that's the most common mistake I see for people doing it that way. All right, so if you add them all up and divide by 7, what do you get? So your average velocity is 12 meters per second. That is not your average speed, by the way. Why did you add up all 7 numbers? You suggested we add up all 7. Why? Just felt right.
Well, you had asked,
I asked what's the average velocity, so why did you want to add up all 7?
I guess just because that's how much data we had. If we were wanting to find the average of, if those are all the numbers we had for velocity, and you want the average of them all.
All right. But why are there 7 numbers up there? Pardon?
Because we only reported 7.
Yeah, but, actually, I'm going to do it slightly differently. Suppose I just gave you the information for every 2 seconds. If you average these up, what would you get? Oh, wow. Why add 4? Why stop there? Is there something special about every 2 seconds? Just like, is there something special about every 1 second? Suppose I did every 6 seconds. What's my average now?
12.
This connects back to when we found average velocity. We took the first and the last and just divided by 2.
Yep.
There's nothing special about 1 second or 5 seconds or 2, whatever the interval is. Now, if you're gonna do it this way, one thing, acceleration needs to be constant, and the time intervals need to be even increments. So this counts as even increment because we did every 6 seconds there. But if I had 0, 1, 5, and 6, then adding them up and dividing, not necessarily gonna work. Although in that particular case, I think it would. So 0, 1, 3, and 6, that would not work. Okay, so let's take a look at this new problem here. It is pretty much the exact same stuff that we've been doing before. The difference is there's some hidden information as part of the language here. So first I'm going to write down the big 5, got my displacement, my velocity, initial velocity, final velocity, acceleration, and time. what do we know?
Our initial velocity,
Is
0,
why?
because it's being dropped. Which
Yeah.
means it's,
So initial velocity is 0 meters per second. And the key word there is dropped. Otherwise, it's called thrown. If it's thrown, then you don't make that assumption, but dropped automatically means initial velocity is 0.
our final velocity.
We don't know.
Displacement,
What's my displacement?
50 meters.
All right, two things here. First, let's address the final velocity. I think Jacob, you said final velocity. What were you about to say about the final velocity?
Well, I've realized now that, I was gonna say it was 0, but when we're finding final velocity, isn't it right before it would hit the ground?
Yes. And that is probably the most common mistake that I see in a problem like this, is people assuming the final velocity is 0, because it hits the ground and it stops. The trouble with that is we have a set of 4 equations for when acceleration is constant. As soon as it touches the ground, acceleration is not constant anymore. Acceleration changes very drastically when it hits the ground. That's what kills you. It's the
So it can stop.
So, final velocity of the falling rock, even though it is usually not stated as what's the velocity just before it hits the ground, oftentimes it'll be what's the velocity when it hits the ground. You're supposed to know that that is the language that they use in physics to indicate that velocity just before it makes contact. All right, we have one other piece of information that is implied in this problem, but not stated explicitly.
Acceleration.
Yes. Now, acceleration, assuming we're ignoring air resistance, if the only force acting on an object is its weight, then the acceleration is pretty much set. Now, it depends on where it is. I did not state where this problem takes place. You probably should assume Earth. However, years ago I gave a multiple choice problem where none of the answers were correct because I never stated where it was. But usually, textbooks don't say it when it takes place on Earth. When the only force is the force due to gravity, otherwise known as weight in this context, the acceleration due to gravity is represented by a lowercase g. This is not g for gravity, it is g for the acceleration due to gravity. Or gravitational acceleration, but either one. Approximately 9.8 meters per second squared on Earth. Mars, I think, is somewhere around 2.7 meters per second squared. The moon's about 1.6 meters per second squared. Jupiter is 27.5, 24.5, somewhere in there, meters per second squared. I know sometimes in pre-calculus, the student will get, it's disguised as just a plain old math problem, but behind it is this. Sometimes they'll use for G 32, that's 32 feet per second squared, or 32.2, a little bit closer. Winston-Salem, 9.798 meters per second squared. That is Winston-Salem specific. In the, I think starting in the 70s, they started to do the experiments trying to figure out what is the acceleration due to gravity throughout the world. And so they had these instruments that are placed various places. For Winston-Salem, the early studies, it was placed, there's that road that tees into Silas Creek right there in the median. At that point, that's where the device was placed. that was the value they got. I'm feeling that's pretty darn close to where we are, the exact same height. So, I'm feeling confident with that. Now, if you're looking at some old lab, it says 9.796 meters per second squared. I just want you to know, I originally miscalculated. I redid it a couple of years ago and realized my mistake. Should be me. The acceleration due to gravity. This g right here is always a positive number. The acceleration might not be, but this is a scalar here. This is the magnitude of the acceleration due to gravity. The acceleration due to gravity is always down. It defines what down is. Down is always the direction of the pull of gravity. If I let go of this, it will fall in the direction of the force, in the direction of the acceleration. So, what is the acceleration in the problem? Assuming it takes place on Earth.
Negative 9.8 meters per second squared.
Why negative 9.8?
Because we're going down, or it's in the negative direction.
All right. Now, if that is correct, there's another mistake on the board. Or if the other thing on the board is correct, that's not right. We have a contradiction here.
Displacement.
Pardon?
Displacement.
Which way was displacement?
Up there it shows positive.
Yeah, so what assumption did you make when you made that positive?
Did it- Yeah, from the ground up.
That we're elevated and
The cliff was tall, 50 meters tall.
So when I let go of this, so I'm on top of the cliff, I let go of it, which way is it going to go?
Down.
So when you say 50 meters here, what assumption have we just now built into the problem?
our starting point.
No, in terms of direction. What is displacement anyway? Let's go back to the definition.
Displacements from where it starts to where it ends.
Okay. And if you have the displacement as positive 50 meters, you have made an assumption. You have established. What have you established?
The starting point.
Not just the starting point. Let me reword this. What is the positive direction?
Anything above 50.
Then what you're saying is Craig was wrong. Greg, you're agreeing with him?
No.
So you're saying Jacob is wrong?
Nope. So I don't know.
Okay, fair enough. All right, Amy, you said something?
Wouldn't like it be positive because it includes the 50?
Wouldn't it be positive?
Yeah, because,
Which is the 9.8 is positive?
yeah, I think, I'm not sure.
And Amanje, I thought I saw you shake your head up and down, or you nodded? Okay. Oh. The nod seemed more confident now, the peripheral, than the I guess you threw in at the end. All right, so let's draw out the picture here. Cliff. 50 meters. An exciting picture, I know. So realistic. The rock starts here and it goes that way. So my displacement is a vector from where I began to where I ended. That arrow right there represents my displacement. If Craig says that my displacement is 50 meters, at that moment he established down is positive. The positive direction is whatever you say it is. Down is positive. So if down is positive, what is the acceleration?
Positive.
Give me the whole thing.
9.8 meters per square positive.
If we had had a negative here and a positive here, well, we'll do that problem in just a second. But we have the three pieces of information. Drop tells you this, the fact that it's falling implies that it's being pulled by the force due to gravity, and so our acceleration is 9.8. The positive tells me that the fact that these are both positive tells me that down is positive. You could have made them both negative also, doesn't matter. Pick one and live with it. The math people brainwash you and think about the y-axis. That's the positive direction, that's the negative direction. We in physics can go, why? Why? We're not stuck in that rut. You can't tell me what to do, old man. So let's solve it, and then let's take a look at what happens if we had done it wrong. So final velocity, what equation should I use? Or if you want to, we can solve for time first, Just know where you want to put the math.
The acceleration times time.
Wait, sorry, which one?
The initial velocity plus acceleration times, the time.
Oh, the VF equals VI plus AT?
Yeah.
The trouble with that is we don't know VF or T.
Oh.
So let's just say that you went down that route. If we plugged into that, the VF equals VI plus AT, we'd have VF equals 0 plus 9.8 T. And at that point, hopefully you recognize, ooh, I have two unknowns here. I'm stuck.
Use the fourth one.
That was the,
VF squared equals VI squared plus 2A delta X.
we're
S.
using S today, so,
Yeah.
yeah. And there should be a dot in between those. It is specifically, it's not just multiplication, it's a dot product. All right, so doing it that way, we end up with VF squared is equal to 0 squared plus 2 times 9.8 times 50. So we're on 23. Let's see if I can do that again. Oh. Oh, somewhere around 32.7.
31.3.
Anyone want to finish it?
Meters per second.
Positive or negative?
Positive,
Why?
because we're still going in the same direction.
Yep. Remember, this equation just tells us speed. You have to think through it to realize, oh, wait a second, I need to find velocity here. And it is still falling officially. So positive 31.3 meters per second. And now time.
Could you use the first one?
This one here? Is that what you're,
Yes.
yeah, now that we know final velocity, or final velocity over there. So this becomes 31.3 equals 9.8 t. T equals 31.3 over 9.8. So around 3.3.
Three point one.
3.1. 19.
Yep.
Yep. Seconds. And now the usual, any questions to hear? All right. So let's now play the what if game. We established 50 meters as the displacement. Suppose acceleration were listed down as negative 9.8 meters per second squared. Let's see what happens in the equations now. This is now a negative here. So VF squared equals negative 980. And so VF equals what?